Hi guys, week 15, we're getting there. This week we're going to look at, we got two lessons a day. So we got 115, 116, and then 117 and 118. So four lessons to get through, but 118 we're getting through 120. So we are nearing the end. So lesson 115, we're looking at relative sizes of sides of a triangle and angles of a triangle. So we know angles of a triangle, whether it's right triangle, equilateral, scalene, isosceles, equilateral, they always add up to 180. And then we know the side lengths obviously are proportional. So we look at this one right here. Actually, let's draw our own. Let's go a little bit more extreme. So this one, let's say we have an isosceles triangle where this angle and this angle are opposite from these sides. Well, these angles are the same because these side lengths are the same. Okay? And then we don't know what these angles are, but we know that this one is our smallest angle. Yeah, just in looking at it, but also this side is shorter. So the side is shorter, so this angle has to be smaller. As we go back and look at, let's see if we can find an angle that we pivot on. So let's look at this top angle right here is the one we're referencing. So as we make it narrower, that angle is getting smaller and the side length is getting shorter. What happens when we move it out? Obviously, this angle is getting bigger and the side length is getting bigger. And we keep going out all the way to we get now a obtuse angle, and it's bigger and bigger. They always add up to 180. So as this angle is getting bigger, then the other two angles, interior angles of a triangle, are getting smaller. Because if they add up to 180 and one's 30 and then it's 40 and 50 and 60 and 70, 80, 90, 100, 110, whatever, and the other angles have to be getting smaller in order for it to be a triangle. So that's all we're looking at here. This angle and all the other angles, but this one's easy to point out when we move this. As it gets smaller, okay, the side length opposite it is getting smaller or shorter as well. So that's kind of what we're talking about when we're looking at this. So if we look at this, we may not know the angle measurements, but side A, okay, or angle A, so side BC, okay, correspond. Okay, C looks like a right angle. We don't know for sure. It's not indicated, but AB is probably our longest side. It's opposite the biggest angle. And then B is not the smallest or the largest, so it's our in-between angles, second largest, second smallest, right here. So the side AC, the side opposite of it, would be the second longest or the second shortest. There's only three sides. Okay, so in looking here, we're given this triangle, okay, PQR. We don't know what the side lengths are, but we know that the interior angles have to add up to 180. So angle P has to be 60 because 60 plus 61 plus 59. So it looks almost like an equilateral triangle, but it's not because it's 60, 61, 59. The angles are all very close, but they're not exact. So opposite side lengths, well, PQ is opposite of the 59-degree angle. Let's go ahead and make sure I have it lining up correctly with what's in the book. Easier for me to draw when versus explaining it all. Just so we know this is 60 because 61 plus 59 is 120. So this side has to be 60 for them, or sorry, this angle has to be 60 degrees for them to add up to 180. So what that tells us is this is our smallest angle, barely, but it's still our smallest. So this opposite side, PQ, is the shortest side. Okay, 60 is now bigger than 59, less than 61. So this is our second biggest or second smallest angle. So side PQ is the second largest side or longest from R to Q or Q to R. And 61 is our largest angle. So it's the side opposite of it, PR or RP would be the longest side length. We don't know what the measurements are of those sides, but we know this is the shortest, this is in between, and this is the longest because of these angle measurements and that property we just showed. So it expands, when that angle gets bigger, the side opposite is getting longer. Again, if we were given the side measurements and wanting to find the angles, at least maybe not the exact measurement, but figure out smallest, middle, largest, we could do that. Okay, so we have 7, 8, 9. So 7 is the smallest. Angle C is across from that, so we don't know what it is, but we know angle C has to be the smallest angle measurement. 8 is next, so opposite of that is A, so that would be our middle angle. And then the largest angle would be B because it's opposite from 9, which is our longest side length, so that would be the order of our angle measurements. Okay. Example 3, if we know length of AC, how could we find the length of WY? Find WY of AC is 6 centimeters. Okay, so let's look at this. So we have 85. So looking at this triangle here, we have 85-degree angle plus 55-degree angle, which is 140. So we know angle X has to be 40 degrees. Over here, 40 plus 85, A has to be 55 degrees. So we could think of this as similar, not congruent. The side lengths are different, but the angle measurements are the same. So a 40, 55, 85 degree triangle, or 55, 85, 40 degree triangle. So X and B correspond, C and Y, and then A and W correspond. So we're looking for AC, or sorry, we're given AC is 6 centimeters, so 6 right there. Okay, we know that these have to be so not perfectly to scale. It's kind of difficult to get these triangle angles exactly where we want, but we have A, B, C, and E. So we found this. This was our missing angle. We found it because it has to add up to 180. This one has to be 40 degrees. So Z and B correspond, C and Y, and then A and W. So we know AB is 8 centimeters. And with AC is what we record. AC is 6 centimeters. Well, then we know the side lengths. Here we have AC. Oh, sorry, I did it backwards. This one should have been our smaller one, but we'll go with it. So this across from our longest angle, this one is 6. This one should have been the larger one. But anyways, I'm not going to redraw it because the property still applies. So we have 8 times a number equals 6. 6 times that same scale factor is going to give us YW. So we could also set it up 8 to 6 equals 6, because that corresponds with 8, to Y. WY or YW. Okay, cross multiply. 6 times 6 is 36. Mm. 36 divided by 8. That is 4.5. So we set up, we know if they're similar, then all the side lengths have to be proportional. So we can set up what we know about proportions, just like when we're doing boys to girls or percent to dollars or whatever it is. We can set up a ratio box, or we can just set up the ratios right away and then cross multiply and divide. Okay, so we ended up with 4.5. So we could have figured out the scale factor and then multiplied it by the side, or we can set up and equal proportions as fractions and then cross multiply and divide. Either way, we're going to get the same answer. Two different ways we can solve that. All right, practice set, we will do that together. Lesson 116, again, 4 that we're getting through today. So division by 0, and I know we've talked about this, you guys probably maybe already know this, but anytime we divide by 0 in our calculator, you can even try it, we end up with an error message. That's because we're not actually able to divide by 0. It gives us an error, or down the road you're going to call it undefined, no solution, something like that. It's just not possible. So in an equation like this, we always say any number divided by itself is 1. That's true, but as usually is the case, 0 is our rule breaker. We can't divide by 0. Even if this is 0, we get 0 divided by 0. Well, we think that should be 1, but it's actually not, because 0 divided by 0. We can't divide 0 by $0. I can't divide it into anything. And then even more of an issue is the denominator being 0. We can't divide by 0 because it gives us infinite. So just a little side journey here. So let's just use 5. If we do 5 divided by 1, 5 divided by 2, 5 divided by 3, 5 divided by 4, 5 divided by 5. What do we notice as we start dividing by a larger number? As the denominator is getting bigger, then our quotient, our solution, is getting smaller. Well, let's do the opposite. 5 divided by 0.5. 5 divided by 0.1. Oops, sorry. 5 divided by, and look at the screen and use 5 divided by 0.5. You get 10. 5 divided by 0.1. 50. 5 divided by 0.01. 500. 5 divided by 0.000000, really small number. It's still greater than 0. It's not quite 0. It's going to give us 5 and then move the decimal place 13 to the right. So a very large number. So as the number in the denominator, what we're dividing by, gets smaller, the quotient or our solution gets bigger. So if we end up dividing by 0, that's why it's undefined, because it's really infinite. We can't do that. So that's what's going on. And as I said, if we do 0 divided by 0, we get an error message because, as it says right there, we cannot divide by 0. So we looked at some of these examples. We used 5. They're using 10, obviously. It's getting further from the origin. The smaller the number gets, under here, or closer to 0, so to speak, then the solution is getting further from 0. Now we've looked at some inverse relationships. Again, inverse relationship. We have y equals a constant divided by x. As we divide by x, obviously y is getting smaller. That's an inverse operation. Just like we saw the example, if we're driving somewhere and we speed up, we go from 50 miles an hour to 60 to 70 to 80, whatever, then our time that it takes to travel from distance from point A to B, that time is going down. So as the speed goes up, the time goes down. Vice versa. As the speed goes down, the time goes up. So that's an inverse relationship. But when we have an inverse relationship and we look at it in a graph, let's just say 5 divided by x, and then we go in and we graph it, okay, we get these two shapes. And it is, we usually focus in for real world examples on the first quadrant, but it also appears here in the third quadrant. And as we notice here, it's getting ever so closer to our x and y axes, but it never actually touches or crosses those. So it's going to as x gets closer to 0, but we can't divide by x, okay, so it's never going to be 0. Okay, so this graph is never, we could take it all the way up to y is a billion, a trillion, whatever. It's going to get closer and closer and closer, but it's never going to cross this axis. Same thing here. Okay, it's going to continue out infinitely this way, but it's never going to cross down into this quadrant. And that's because we go back, well, we can't divide by 0. Okay? And then we never have 5 divided by a number that's going to give us 0 or give us, if we divide by 0, it's going to give us infinity. So we're kind of in between. It's going to get infinitely closer, but never touch or cross. That's what we're talking about there. All right, so going way back, we talked about fact families, like 2 times 4 is 8, 4 times 2 is 8, 8 divided by 4 is 2, 8 divided by 2 is 4. Okay, we have all of those multiplication and division facts that we can make out of 3 numbers, but we can't do that when zeros apply. 2 times 0 is 0. That is true. 0 times 2 is 0. That's true. 0 divided by 2 is 0. That's true. But if we go 0 divided by 0, that does not equal 2. So again, 0 is kind of our rule breaker, so to speak, that it doesn't work out to be true. All right, so if we're asked to graph this, okay, we can graph it. It's going to be an inverse relationship because as x is getting bigger, we're going to be dividing by it, so y is going to ultimately be getting smaller. Okay, so let's go ahead and plug in. Let's get that one. What was it? 12 divided by, let's use our parentheses, so it's not just dividing by x and then adding 2, it's doing x divided by x plus 2. I believe that was our x plus 2. So we got 12 divided by parentheses x plus 2. Because if we don't do parentheses, it's just going to be 12 divided by x and then add 2, which isn't the same as all of this being in the denominator. So we got it in correctly. We hit graph. Again, that plus 2 has shifted us over, but still it's going to get infinitely closer. So what can it not be? And if we draw, I don't know if they'll let me draw a vertical line here, but the reason it's going to get closer now to -2 and never cross that versus the y-axis is because, go back to this, well, what can x not equal? Well, 0 plus 2, that still works out fine. So x can be 0 in this example, but it can't be -2, because -2 plus 2 is 0. We end up with 12 divided by 0, and we can't do that. So usually we do it as this, that's undefined. That 0 with the slash through it means we can't do it. So if we go back to our graph that we're looking at, and we go into our second graph into our table, and what do we get? Oh, well, at -2, what is that? We get an error message. So x can be -3, -4, -5, -6, all the way to -infinity. It can be -1, 0, 1, 2, 3, 4, 5, 6, all the way to positive infinity. But there is one value that it cannot be, and that is -2, because that would give us -2 plus 0, or sorry, -2 plus 2, which equals 0. 12 divided by 0 doesn't really matter what's in the numerator, but we can't divide by 0. So that would throw that off. So that's why that error message doesn't mean you did anything wrong putting it into your calculator. We input it correctly. It's just that actually is true. We can't have -2 in for x, because that would cause us to divide by 0. Okay, we look at this practice set together and go over it again. Concept I know we've talked about, now we're just kind of hammering it home that we cannot divide by 0. All right, lesson 117 is a little unique. It talks about significant digits. So this one, again, just kind of looking at, if we're looking at a ruler, let's say we're using a ruler or tape measure that's in centimeters, 8.9 centimeters. Okay, we use 2 digits to write the length. We use 1 decimal place value. The rule is divided into tenths. So 1/10, 2/10, 3/10, 4, 5, 6, 7, 8, 9/10, 1 and 1/10, 1 and 2/10, 1 and 3/10, or 1.4, 1.5, 1.5, 1.6, continuing all the way up. And so those are our significant digits. Obviously, there's you could break it down further and further and further. There's you can be halfway between one of those tick marks. You can be halfway between, or a third of the way between those tick marks, or 0.25 between those tick marks. But we use these two to distinguish it. Okay, so those are significant digits. All right, so let's read through this just because it can get a little kind of complicated to understand what we're talking about. Just think about kind of what is necessary in our description. And when we're talking about how many, let's say, how many miles is it from here to the nearest planet? Okay, we probably won't use miles, yards, feet, inches, and maybe there's some scientists or some methods out there where we would probably just round it to the nearest mile, because to start breaking it down to 1/4 of an inch, 1/8 of an inch, 1/16 of an inch isn't really necessary with that big of a distance. So to measure the segment at the beginning of the lessons, we compare it to the length of standard scale. We are confident that the segment is about 9 centimeters. We also know that the segment is about 8.9. However, we cannot say with confidence the segment is 8.916 centimeters long. So again, our tick mark is at 8 centimeters, 9 millimeters, or 8.9 centimeters. And then 9 centimeters, we know it's right around there, but we can't say, because there's no internal tick marks between the millimeters, to say that it's 8.916, because it doesn't get that precise. Now, again, depending on what it is, there are some computer programs that take things that need to be very precise. They might take it down to 1/1000th of a centimeter or an inch or something like that. But for a lot of things, if you're cutting a board to build a fence or something, you probably need it to the nearest centimeter or millimeter, or talking about inches, to the nearest 1/8 or 1/16th of an inch. The number of digits we use to express a measure with confidence is called the number of significant digits. So 8.9, there's 1, 2 significant digits. Below are rules for counting significant digits. Count all the non-zero digits. So 2.54, there's 3 significant digits. It could go 2.5400000000, but those zeros are not significant. Count zeros between non-zero digits. So 1, 0, 7, 10.7. We don't say those are 2 significant. So if it was 1.7, it'd be 2 significant, but it's 10.7, so there's 3 significant digits. Count trailing zeros in a decimal number. So the decimal 1.20 has 3 significant digits, but if we call it 1.2, like we're saying $1.20 or something, 1.20, there's 3 significant digits. If we're just saying 1.2 for whatever, then it would have 2 significant digits. Do not count zeros if there is not a non-zero digit to the left. So this is where it gets a little tricky. So the number 0.023, we say has 2 significant digits, even though it looks like there's 1, 2, 3, or even maybe 1, 2, 3, 4 significant. Trailing zeros of whole numbers are ambiguous. The number of significant digits in 1200 could be 2, 1, 2, 3, 1, 2, 0, or 4, 1, 2, 0, 0. Again, expressing a number in scientific notation removes the ambiguity. So 1.2 times 10 to the power of 3 would have 2 significant digits, but if we include the 0, 1.20 times 10 to the power of 3, now we say it has 3 significant digits. So again, a little wordy and maybe a little confusing. So let's take a look at some of their examples. State the number of significant digits in the following. So the diameter of a quarter is about 2.5 centimeters. 1, 2 significant digits. A ruler is about 30.5 centimeters long. We have 1, the zeros in between significant digits, so it's a significant digit. So 1, 2, 9.3. 9.3 times 10 to the power of 7, that would be a lot of zeros, but in scientific notation, that makes it really nice to identify. We have two significant digits, 9.3. A mile is 5,280 feet. So that was the last one we talked about. Exact numbers have an unlimited number of significant figures, so we do not count any digits when dealing with exact numbers. Exact numbers include counts and exact conversion rate. So if we're using a unit multiplier, that one's kind of tricky because it looks like there's 4 or 3 at least, but we say it's unlimited. Right, so let's look at this rule. A product or quotient, so we're multiplying or dividing, of two measurements may only have as many significant digits as the measurement with the least number of significant digits. So kind of a little wordy and maybe confusing, but here's what they're saying. 8.9 divided by 4. So I have two significant digits, I have 1. When I divide, I end up with 1, 2, 3, 4, but since we started with 2 and 1, 2 is greater than 1. So we're going to say that there's two significant digits, and we're going to round it to 2.2. Just like if we back to the beginning where we had the 8.9 centimeters on a ruler, so we measured that out and we wanted to divide it into 4 parts, and we would divide it into 2.2 segments, because 2.225 is too exact for that ruler or that measuring tape of what we can accurately measure out. What is the volume of a cube with 1.2 millimeters long? So 1.2 to the power of 3, it's a cube. Side to the power of 3, or edge to the power of 3 gives us the volume, so 1.2 to the power of 3 gives us 1.728. But when we're talking about significant digits, so this is only for this lesson if it specifically says significant digits. If you see this test question and just ask for the volume, put this. More exact the better, but for significant digits, this introduction, we can leave it as 1.7. Because this one had two significant digits, so our solution has two significant digits. Another rule, a sum or difference may show no more decimal places than the measurement with the fewest number of decimal places. So if I have 6.24 and it's heated and there's 4.6 milliliters after it was heated, how many milliliters of liquid evaporated? So we would find the difference in those. 6.24 minus 4.60, well, I have 3 significant digits. I have 2 right here, so 2 is less than 3, so I'm going to end up with 2. We're not going to say 1.64 milliliters, we would just say 1.6. So again, this one, it's not overly difficult, it just kind of is confusing for the sake of just being confusing. We'll go over it more in class. Again, this is only if it says significant digits. If it's just a regular problem where it just gives you this, and then think back, okay, which place value do I have to knock off? I have 3, 2, 2, so do I go to 2 or do I go to 3? We need to know for this lesson, and it's not unimportant, but don't let it confuse you when we're just typically solving problems. This is just when we're doing units where it only makes sense to take it out to the tenths place or the hundredths place or whatever, kind of like we do with money. We always automatically round to the nearest penny, which is 2 decimal places. We kind of do it without even realizing it. So money, we always have those significant digits, even if we don't realize it. All right, and then the last one, we're looking at sine, cosine, and tangent. I believe we already introduced this, but the ratios that we're going to use, so what this is, let's draw it. And then this applies for so this is, we're talking about a right triangle. So we have sine, cosine, and tangent. We usually use these 3 letter short names just and that's how it is on our calculator. I'll show you in a second. So if we're looking at, let's look at angle A as our reference angle. So that's where we're starting. So the hypotenuse, so a way we can use it is this acronym, or just kind of like PEMDAS, or please excuse my dear Aunt Sally. A way we can remember sine, cosine, and tangent is SO, CA, TOA. I'm not sure what that means. So we're looking at sine of angle A, so OH, opposite, okay, and hypotenuse. So opposite, we don't have to write this out every time. This is where we're remembering this. So opposite over H, hypotenuse, okay, which is across from the right angle. So the hypotenuse never changes. But in reference angle A, what's opposite from it? Well, it's this side right here. So this is it's a terrible 3. So let's say this is a 3, 4, 5 right triangle. So this is the opposite of A. And so we would say 3 over hypotenuse 5. Cosine of A. A is for adjacent. And then the H still stands for hypotenuse. TOA, and opposite over adjacent. So let's take a look at that. So still looking at angle A, cosine, adjacent. Well, I have 5 and 4 adjacent to it, but 5 is the hypotenuse. That's how I know this side is the adjacent side. So 4 over 5, and then tangent of angle A, okay, opposite over adjacent. Opposite is 3 over the adjacent, which is 4. Okay, so it's going to have those relationships. So ca, to, sine, cosine, and tangent. So help you figure it out. We also have, we'll show you the calculator here in a second. So opposite over hypotenuse, that's where we got so. Cosine, adjacent over hypotenuse, ca, and then tangent, that's where we got TOA, O over H, or sorry, O over A, TOA. We just did an example of this, but let's say it's 8, 6, 10 triangle, so we just doubled the triangle we were looking at, scale factor 2. We went from 3, 4, 5 to 6, 8, 10. We're looking at angle A here. 6 over 10 sine is opposite over hypotenuse. 6 over 10 is 0.6. Cosine, adjacent, 8 over hypotenuse of 10 is 0.8. And then TOA, tangent, is 6 over 8, 0.7. Okay. Notice that we express each ratio as a decimal. The trig ratios for this angle happen to be rational numbers. Since many angles involve irrational numbers, the trig ratios for many of those angles are irrational. We express the irrational ratios rounded to a selected number of decimal places. Okay, so looking at this one, find cosine, sine, and tangent of angle R. So we have 30, 60, 90 triangle, and then we can go back to those ratios that we talked about a while ago, and I let you guys write it down on your reference sheet. But again, 1 to root 3, because 1 squared plus the square root of 3 squared is 4, square root of 4 is 2. So that's where we get this relationship for 30, 60, 90 triangle. So the sine of 30 is 1/2 of 0.5. The cosine of 30 is the square root of 3 over 2, and then the tangent of 30 is 1 over root 3, which gives us, again, if the rational numbers in our division, then it's going to give us an irrational solution. We can also use our calculator. So it's 30 degrees. So you got your calculator in front of you. There's these buttons that you probably never use. Maybe you never even noticed. We have them right here: sine, cosine, and tangent. TA84. So what we can do, what we just did, okay, we have the sine. Just hit SIN, sine 30. That gives us 0.5. Same thing we got when we did it by hand. The cosine of 30 was that irrational number that we rounded to 0.8. 0.66, I think is what the book rounded it to, and then the tangent of 30. We take it out that far. Now we can also use this to work backwards to find angle measurements. So let's say we know the relationship. Let's just take this last one and let's do second tangent. So the inverse of that, and then this versus punching in that manually, let's just do second negative symbol. That'll give us the answer that we just had and bring it down there. So the inverse of that, if we know the relationship, the decimal or the fraction or whatever, we can do second tangent, cosine, or sine to work backwards to find the angle measurement. So this will be really handy down the road where you're not given, to this point we've been given 2 angle measurements and we have to find a third. Well, we know they always add up to 180, so that's not overly difficult. There'll be times where you maybe know a couple side lengths and one of the angle measurements, and you have to work to find the other angle measurements, and you can't just say, well, 2 angles added up equal this, subtract it from 180, and there's your third angle. We're going to have to use some of these trig properties in order to find those. So that's our abbreviation. That's how it shows up on our calculator as well: sine, cosine, and tangent. So I usually just write SIN and call it sine. I have to use cosine and tangent, same thing. I just use those shortened versions. All right, so find cosine, sine, cosine of angle A. So if we go in, we hit sine, just like we showed you, of angle A is enter 35, or ours we do it opposite. We do sine of 35. So we do sine 35. You can't see sine 35, and hit enter, and there's our relationship. So the sine of angle A is 0.574 if we round it. We can also do the cosine in there, and then we know the hypotenuse, so we can work backwards. The sine of 35 equals what we got right here, or in our calculator. It goes on forever, so you're gonna have to round it off at some point. We round it off here, divided by 1, or the cosine here. Okay, so why would we use this? Well, let's say we're surveying something, or we talked about indirect measurement in the past. A tree, maybe it's difficult to get to something we're measuring to, a tower, a tree, or something. It's a heavily wooded area, or whatever the case may be. Or we just don't want to climb a tree and use a tape measure. We want to calculate it to save ourselves the risk of injury. So we know the angle is 22. We can calculate that by angle of sight with the ground, 22 degrees. We know tangent is TOA, opposite over adjacent. The distance is 100 feet away. We could use that with a tape measure, a rangefinder, or whatever. That's pretty simple to figure out. And we can calculate the tree height. So we know the tangent is 22. We can go in and find tangent 22, tan 22 in our calculator. Okay. The opposite is the tree. And we make a right triangle, so the tree straight up and down. There's a right angle right there, so the opposite. Okay. And then the adjacent, which is what we know. We can use the hypotenuse. We could say, use one of the ones with the hypotenuse. The only difference is we don't know this distance right here. If we were able to use, again, a rangefinder or something to exactly measure the top, but this is going to be difficult to measure. This one that runs flat with the ground is going to be the easiest measurement. That's probably why we would use tangent. So opposite over adjacent, the tree height over 100 feet, we get 0.04 over, the tangent of 22, which it gives us that, and that's why they rounded it off to 3 decimal places, 0.404. The tree height over 100, t over 100, equals a tangent of 22 over 1. And then we cross multiply and divide, and we get 40.4 feet. All right, and we'll do this one together, and that'll be it for this week. Good job.